presentation.
Okay, thank you very much for all of the organizers of the program and of this workshop in particular. So this is joint work with Brent Duran, who is still at ETH Zurich. So I just recently moved from ETH Zurich to University of Copenhagen. Brent Duran, he's an algebraic geometer at ETH, and well, he stays there. And then there is my former PhD student, he just finished, Michael Walter, who will in a few weeks take up a postdoc position at Stanford in Patrick Hayden's group in the physics department. So he'll be close by. Well, since I just moved to Copenhagen, so there are some possibilities for a PhD and postdoc. If you're interested, or if you know someone who might be interested, just get in touch, maybe I'll be. Okay, so what's the setup? Well, I got 3 parts for this talk. I want to tell you about the setup and maybe give you a brief motivation. The next thing is I want to tell you about our result. And then I hope to tell you as much as possible about our proof. Let's see how far we get. But maybe the high-level overview of the high-level overview. Excellent. So what's our setup? So we got 2 compact connected Lie groups. I'll give examples a bit later. G and H. Okay, so this is these are compact connected Lie groups. Just think of any sort of unitary group you have in mind anyway. That will do for this talk. I'm not an expert on Lie group theory, so I will try to stick to the unitary group. Make it easy for all of us. So there was, we're going to take, I'm going to have some group homomorphism from this small group, that's my little group H, into the big group G. And I'm going to fix it. Sorry?
F is injective?
No, not necessarily. It's just a group homomorphism.
Why is H smaller then?
It's thinking that way.
Well, just psychologically.
Psychologically smaller, right? You'll see in the examples that it kind of looks smaller. Okay. And then we want to look at something that's known as the branching problem that we have been discussing at great length. I have to be slightly pedantic about the notation, so I hope I do this. So I take a representation of G with highest weight lambda. So that is the so-called highest weight. Again, examples will come in a minute. I'm not going to. So that's the highest weight lambda. And I like to write lambda is in G hat. That's sort of the set of highest weights. Labeling this, it's a very natural way to label the irreducible representations of G like that. And I'm going to take that representation, which is a G representation, and reduce it to H. Right? When I write a down arrow like this, I mean via this group homomorphism. And that then will decompose into a sum of irreducible representations of the group H, again now labeled by some highest weight mu, which is now a highest weight of course H, right? And that may come with some multiplicity. So we have this multiplicity space here, which is indexed by lambda and mu, but I'll try to keep track of F as well for the moment, okay? Because it all depends on how this thing is embedded. And now you know that we've seen this many times, but for the people who haven't seen it as many times, we are very sloppy, right? Instead of writing the vector space with this dimension, people just write, M lambda F mu. Okay, let's go to some examples. Some examples. Okay. Example number 1 is G is the unitary group in dimension D, and H is its maximal torus. So I'll sometimes denote it, by TG. And this is just U1, 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 D times. And now if I take an element from that group, right, that will be, U1, U2, up to UD. These will just be phases, right? E to the I phi 1, etc. And the homomorphism I would like to look at is just the embedding as the set of diagonal matrices. U1 up to UD, and then zeros on the off diagonals. That's my F, okay, for this example. Now, what are the highest weights? Well, we've seen the highest weight for unitary group a lot already. They're given by a set of integers that are non-increasing. And for the purpose of this talk, I'll just restrict that they're also positive. So we'll look at a polynomial representation. And I will use the following notation. So I will, if I sum them up, that will give n. And this is d. So we can nicely represent this in a so-called Young diagram, which we've seen as well. And here is an example. If d is equal to 3, then this diagram here would correspond to the diagram 4, 3, 1. And if the dimension would be higher, then there would be additional zeros here. Right? Okay. And if I draw it like that, it's, this is the number of boxes in the first row, is lambda 1, that's 4, number of boxes in the second row, and so on. And I'm going to use Peter's notation that lambda dn, which just means lambda has at most d rows and exactly n boxes. Okay, these are the highest weights for this, so this is the way you may think about it. And here the highest weights actually are for each of these u1s, we have a mu I, which is actually from z, but we're going to take it from the positive numbers, positive integers again. And then I could assemble all these in one vector, and this is n mu1 to mu d. Right, you can see that the U1 case is a special case of this case, just with a diagram with one row. Okay, so in this case, the branching problem is well known, and the result are the so-called Kostka numbers. In this case, these are the Kostka numbers. And because we're going to use them later, I'm going to call them K. Okay? It's not the Kronecker coefficient, it's a Kostka number. Okay, and they're given by the number of, and this you remember maybe from a boot camp from Christian's talk, by the number of semi-standard Young tableau of shape lambda and content mu. This means that if I take my example from before, then I could, for instance, have the following one. If I take as content 2, 3, 3, then I can see, for instance, here, I could have this diagram, or I can put the guys like that. And then I get 2 possibilities. So the Koska coefficient in this case is 2. Let's go to the next example. I'm going to do a lot of examples. I think maybe it's useful after all. The next example is UD plus D.
Yeah, why is the mu's not arbitrary integers?
Sorry?
Why are the mu's arbitrary?
Yes.
Well, because I just have a direct sum here. I just have U1 can have any weight.
But
This is
why
just the
are they-
weight.
Why are they not? Why are they positive?
Because I choose them to be positive.
You're
Or-
looking at. You're only.
I'm
looking-
just looking at the positive one. Yeah.
Okay. Fine, because there's certainly
If
ability.
your lambda was a partition, you will only get positive 1 to inverse 3.
Same for the
It's a polynomial representation I'm looking at.
I'll tell you what it is.
I'm sorry, I would like to do that. Otherwise, anyway. I think other speakers have done the same. But I think it's still easier to think about UD than SUD. If I do this with SUD, I get a headache the whole time. So here I have 2 unitary matrices, right? 2 D by D matrices. And I'm going to send them like that. And okay, very good. This gives me also a coefficient. Can I get just a show of hands? How many people know what the branching coefficient is? You don't have to say it. Just show your hand. How many do you know what it is? Okay, very good. This is also the little Richardson coefficient. Just wanted to see if I'm too basic. This is also the little Richardson coefficient. It's nice actually to sort of do this exercise and show that it's equivalent to maybe all the other definitions you've seen. Okay. And the Ledward-Richardson coefficient can also be seen as a number of hives. And again, I think there are a lot of experts in the audience that know much more about it than I do. And I also don't have to really tell you why it's important. We've already seen in the previous talk how it may impact GCT or how it's just interesting in itself. I don't know who told me that, but they're sort of like binomial numbers, I was told. Just like some other object that appears in all sorts of different branches of mathematics, and it would be nice to understand it better. Also, maybe one thing that's relevant here is that we've seen this in Ketan's talk. The Little-Richardson coefficients are extremely well understood, and they have a lot of properties. A lot of things have been proven about them, and a lot of the conjectures in GCT for the Kronecker coefficient, I believe, are just kind of like let's see. Maybe it's the same as for the Little-Richardson coefficient. It may have the same properties. So I think this gives a lot of motivation for what goes on in the GCT conjectures, or at least in the ones that play a role in the Kronecker coefficient. So the next example is U of D times D, and I'm gonna put U D in there by taking this pair of matrices and by doing this tensor product. You all know what it is. This you may also think of just as, having U 1, 1 here, and then take the first entry, and then UB here, and then you do UA1 to UB, 2A, UB, U2 to UB. Okay, that's that action, and I think I'm also not hiding much. So I have here 2 diagrams, mu A and mu B, both with maximum D rows and N boxes. You see that here the degree is preserved. So here I have N, which is of D square, and then I get a coefficient here, which I write as G upper lambda mu A mu B, and this is the Kronecker coefficient. You can show that this is the same using Chauval duality as the normal tensor product decomposition of the symmetric group coefficient. Now I first came across this thing because I tried to solve a problem in quantum information theory, and then sort of I thought I had solved the problem because I thought everything was known about it, and that wasn't the case. So now I'm here trying to figure out what is going on with this Kronecker coefficient together with you guys. And of course we know it's important in GCT. We've seen this all along. I prefer, and this is my example 3a if you want, maybe I still managed to put it below. I prefer a different version of the Kronecker coefficient and make things a little bit easier. Namely, I want to make it more symmetric. So I want to actually consider ud cubed and then injecting 3 triple factors just in the natural way. Right here you get UA tensor UB tensor UC. And then I would like to restrict to the diagram lambda, which is just one row with n boxes. And then you can show that the corresponding coefficient that you get, right, basically the one row coefficient with mu A, mu B, mu C, that is actually just exactly the same as the thing as if you put mu up there. At least if, with the row lengths, with the number of parts, I will not go into that too much detail. There's a fourth example. Okay, this is one of the motivations. There is a fourth example I'd briefly like to mention. I'm just going to eat my time, namely the plethism. Right, plethism also fits into this picture. Namely, you take a matrix from here and you send it via an irreducible representation with highest weight nu to some matrix on that space, and then you look at a highest weight of say degree n, and then you look for the coefficients that appear. So that is the same as like taking the lambda, of the group G, and then looking at through this representation, right, of the group A that thing is acting, and then as an H representation that thing decomposes, and the coefficient here I will denote by lambda, and I'll fix, this map F here is fixed. Remember, F is fixed. I'm not going to write mu for the moment. But because this F here was specified by this irreducible representation nu, I just put nu here, and that gives me my decomposition. So the plethism also fits into this picture, but remember that this nu is fixed in my talk, right? So this F is like a fixed thing. Of course, we know they're important for GCT. Let me just mention that their plethism coefficients are also important to understand the properties of indistinguishable particles, for instance, fermions, bosons, and generalizations of the Pauli principle. So there is some relation. There is an exercise. If you'd like to do that, we've already seen it in a little bit in Nicolas' talk, namely that case 1 is a special case of example 1 is a special case of example 2 is a special case of example 3 is a special case of example 4. That's sort of a kind of nice exercise to kind of get going on this subject. So let me tell you something about complexity, what we know about them. Now we want to compute them, right? So better understand what's known about them. So first of all, what's the input? The input is, in one case, a diagram. And I put now D for sort of the dimension of the big group. Right? I think always of a big group and a small group. Capital D for the dimension of the big group. And let us give n boxes. And the mu's, mu again is a partition. And in the examples you've seen, I'll gloss over this a little bit. Mu was like one partition, or maybe it was several partitions. Now, what is the input size? What's the size of the input? Well, the input is presented to me as a sequence of integers, each of which I can encode in a bit string. And if I assume that the total number is n, then also the maximum number for each of them will be n. And therefore, the input size will be d numbers times logarithm of n to encode their length, plus, and then maybe order d of log n for encoding the mu. So that's the input size. Then I can ask myself, what's the complexity of... Yes, for the moment I will just, yes. For the moment that's okay, but for the actual kind of result it's not the case. It's more generally true. So, but just for this exposition I think it's sort of nice. So fix this f, right, as we did before. And you have lambda and you have mu, and the task is to compute. And then we have a few problems that we would like to compute. Let me give you this table. I think it's nice. So first of all, of course, the Koska numbers. What's known about the Koska numbers? Well, we got the Koska numbers. We got the Littlewood-Richardson. We got the Kronecker. And we got the Plathysm. And I think because of time constraints, I'm not going to talk about the Plathysm. So we can either ask, let's compute this, or we can ask, let's decide if this thing is non-zero, or we can ask a simpler question, fix f. Okay, f is fixed. And then compute this. F's not going to change, f's not part of the input, f is just fixed. Compute. So what's known? The Koska numbers have been shown to be Sharpe hard by Narayanan, and this implies, that all of them, including the Plathysm, are Sharpe hard because they're special cases of each other. Then the Kronecker has been shown to be in gap P by Bürgisser and Iggenmeier. So it's in gap P. Actually, we're not going to talk about this, I don't know. And the Littlewood-Richardson, we actually know that it's in Sharpe P because of, I guess, this. There are many results that will imply that. And the Koska number, I don't know who first showed that this is in Sharpe P, that you can count this, but maybe Littlewood or something. Now, I think that's known. You see this is a hard problem, computing. It's right, it's a counting problem. Maybe Kronecker is even harder than the others. Deciding non-zeroness is significantly easier. And here, this is shown to be in P. This is a result due to Knudsen-Tau saturation conjecture plus Malmolay. I think you observed that this sort of works in that setting. And of course, that implies that the Koska numbers are in P. And then Malmolay's conjecture, right? He conjectures, this is the conjecture that also the Kronecker is in P.
Koska in P was known before it's independent of that. Koska.
I'm sure. Yeah, I mean, maybe Littlewood also did it.
Gale-Reiser theorem.
Yes,
Gale-Reiser theorem. Very good. Gale-Reiser theorem implies that. So we're just going to put it independently in P.
What did Gale-Reiser got to do with that? It's about the existence of 0-1 matrices with prescribed marginal distributions.
Oh, is that the same thing as Christandl?
Okay, guys, let's do it later. So, this is also known to be in FP, so you can compute this. When you fix F, you can compute. I just learned that I should use FP for functions that I want to compute in polynomial time, rather than decision problems, because P only contains decision problems. So these are functions that I can compute in polynomial time. This is due to Cauchy, I believe.
What is the last column?
This is fix F. F's fixed.
What is F?
F is the homomorphism. In the Kronecker problem, it would be the row length. Okay, fixed number of rows to be 10.
Okay.
1,000, whatever. This here is also Cauchy, and I think Deleuze and McAllister. So today I want to show to you, well, at least I want to state that these two things are also in FP. And a number of other problems. And
Wait just a minute, I want to understand the statement. So all the partition lengths are of the rows
Fixed.
The heights are fixed, is it?
look, F is fixed. F is a fixed homomorphism from here to here. This means the number of rows in the Kronecker is fixed. Okay, for all three partitions, number is fixed. Or in the plethism, the inner plethism is fixed. So the number of rows for lambda and mu are fixed.
Both A, G, everything is fixed there, right? When we say F is fixed, of course.
When I say F is fixed, H and G are fixed. Yeah, so F comes with the groups, you know. Yeah. But in our kind of, if you want to think about the Kronecker, it just means bounded row length, bounded number of parts in the partition.
What is the meaning of the star? You're saying F.
Oh, that was because we're going to do it today. I'm sorry about this. Okay, so today, whatever. Today.
Okay.
What was the today star? Okay. Well, for our setup from before, remember F fix and the setup from over there with H and G. In the abstract, in the general sense, you take lambda in G hat, and you think of lambda as being presented as in terms of its highest weight, in terms of its fundamental weights, as a linear combination of the fundamental weights. Same for mu. Mu is also presented in terms of its fundamental weights, and then the input length is just, if you just assume, let's put all of these smaller than, all of the bi and ni smaller than n, then the input length is just, in this problem, is just log n, order log n. I have to be precise, right? And then our little theorem says that m lambda f mu can be computed in poly log n steps.
So in Kronecker coefficients, all the rows, etc., specified in binary, right?
Yes.
Yeah.
Yes. Yes, specified in binary. You have a fixed number of these binaries. And then, of course, the corollary for the Kronecker is exactly that, fixed D, and then you're given these three partitions, the partitions of n, then G mu can be computed in polylog n steps. Similar thing holds for the plathism. So I have a few remarks. Of course, if I can compute the Kronecker with bounded depth exactly, then I can also decide positivity for it for a fixed number of rows. Right? So in some sense, I mean, in some very weak sense, this sort of settles Monmouth's conjectures for the case of bounded row length. In fact, this is parametric. It's strongly polynomial times it's parametric in lambda and mu, but I won't have time to say something about it. And there are very exciting improvements and better analysis of our things by Panova and Pak very recently. In particular, they can improve the deciding non-zeroness. They can improve this to linear time. Unfortunately, without telling us what the coefficient is in front of that. But nevertheless, it's very nice.
What if you
Can you do it
allow
Checking non-zeroness for the quantum.
number of rows to grow, but very, very slowly?
I don't know. It grows like I think it's like you have to in Panova's paper, Pak Panova paper, it's very precise. I think it goes like power dimension cubed, maybe even a little more.
Well, for GCT, it's like logarithmic.
How it works is writing down the generators of the semigroup and then checking.
You mean checking non-zeroness or checking or computing?
That's what they do.
Maybe let's take it later, because otherwise I won't even be able to tell you what the sketch of the proof is. Let me also tell you that this is fast in practice. So we did implement this for d equals 3. You can do, like before, if you use normal methods, you can do maybe 100 boxes, but then you really have fast hardware. With this, you can easily do 10 to the 8 boxes. Maybe even more. So it's very easy to. And there is this website. So if you want to download the code, play with it, Michael Walter, he programmed this, and he has this website, leadspeak.org. You can also go to my homepage. There's a link to that website where you can see all the information about it and some examples.
Is this Leadspeak or LEadspeak?
Yeah, it's some geeky thing. I don't know. Anyway, so if you go to my homepage, there's a link to it. I think Google will correct it if you mistype Leadspeak. Oh.
It's not Let's Speak, so Leadspeak comes from the lead.
Okay, proof. How much time do I have?
50 minutes.
Ah, very good. So the proof proceeds in 3 steps. Okay, we're going to start here on the right. We're going to put our big group G. Then below it, we're going to put the little group H. And remember, we got this F here. G acts on, an irreducible representation with highest weight lambda that we want to decompose according to this F, right? That's what we're going to do. So here's our procedure. So we're going to first understand what the weights look like, what the weight multiplicities look like of this big group. Remember, TG, these are just the diagonal matrices in G, right? For us, G is kind of like the unitary group. It's the maximal torus. And then for H, we can also choose such a maximal torus. And if you're sort of a Lie group person, then you make really sure that we have to make sure that this sits inside here. Okay, we're going to choose TH so that it's a subset of TG. I always thought this was sort of obvious, but right. So think about the Kronecker for a moment, right? You got the diagonal matrices on D cubed, and then you're just going to inject like diagonal matrices, D by D diagonal matrices. This again gives you a diagonal matrix. So it's just a very natural thing. These are the diagonal matrices for the small group products, like of the diagonal matrices, and here you have the diagonal matrices for the big group. Okay, so this is going to be step 1. Then we're going to go, we want to solve that problem, so we're going to go around that diagram like this. We're going to do from G, we're going to reduce, we're going to understand this branching problem, namely, of course, right, TG is of course a subgroup of G, so I have also a branching problem from here to here. This is a subgroup of that, I have a branching problem from here to here. And then I somehow have to understand how I get back from having understood this to understanding the multiplicities here. These are the 3 steps. Are there any questions to that right now? Good strategy. Let's right. You know what? You know what this is, right? This was our first example. These were the Koska numbers. So the multiplicities here, so if I decompose VG lambda into representations of TG, then this is the same as direct sum over, and now, excuse me, I will label them by beta now. Okay? Before we labeled them by mu, but now we label them by beta. And then I have the Koska numbers here. Beta. And then V, TG, beta. Now, TG are the diagonal matrices. This is an abelian group. The irreps of this diagonal matrices are, of course, one-dimensional. And this Koska number we know, and the Koska number, remember, that was the number of ways of putting semi-standard Young tableau with a certain content. We haven't got it on the board anymore. But what I can do is I can write the K in the following way, and that's important. I can write it as a so-called partition function. So I can write this as kappa. Oh, is that okay? That's a kappa. So I can write it as the number of points in the following polytope. I can take KIR, that's a set of variables, integers, positive, non-negative integers, and then I can say, well, imagine, right? What this means. This is the number of i's in row R. Okay. So I'm going to put the number of i's in row R, right? But if I got weight beta, right? Beta was beta 1 up to beta d, then the number of ones have to sum up to beta. So if I sum up over all the rows,
could you show a little bit? Because
it's okay.
It's just we don't see, at least I don't. Okay.
This is equal to beta I, and then oh, sorry. Yes. And then also, if I sum over the number of over the same row, right? I need to get the number of ones in the first row plus the number of twos in the first row, and so on. That adds up to the number of boxes in the first row. So if I sum up over all these things here, I get lambda. What is this? Lambda R, I guess. Okay. So this here is a so-called partition function, and it can be evaluated in polynomial time.
There's more than just that. You have the column conditions.
Sorry?
The fact that columns have to be strictly increasing are not encoded in that guide.
I think it's okay.
It's not height, it's always not height.
It's always.
No, he's talking about the number of ways to fill a young catalog.
Yep. With a certain content, and the content is given by beta. And I just count the number of.
But when is the
I don't, he has to be semi-standard. There's a
What
semi-standard
is the
condition
form
still.
of this
He just says that
matrix?
his condition is content, and there's a little more. Like,
Right.
for instance, you have to imply that all the ones are in the first row.
Yeah. So I put so my notation is the following. I'm going to look at like row R. Okay, that's going to be row R, and that's going to be, and I'm going to look at the number of ones in.
Row R. Yeah, that's what you said they were.
Oh, do I need more
Anyways,
conditions?
but it's a polytope, I think. You just don't have the inequalities written down properly.
Sorry, I forgot something. Okay. Well, you're right. Yes.
Isn't this the same thing you said before with Gale-Reiser, that you want to take the integer matrices with row and column sums given by lambda and beta?
Yeah, you could do that.
Yeah, you're right. I mean, I have to have the ordering constraints, right? So they go up in each row. I forgot the column constraints, I guess. So the column constraints are that I guess the number of
Yeah.
There's some column constraints, okay?
There's
There are inequalities, and I'm going to put some slack variables to make them equalities.
there's essentially like the dominance of
Yes.
sequences. That,
Okay, I apologize. Okay, upshot is it's the number of kappa in the set D, and then there is some map that takes this vector kappa and it should spit out beta and lambda. Okay. Well, anyway. So
what the proof strategy, you're going to finally reduce it to counting number of
points and polytopes and then taking finite differences. That's right.
constant dimension, is it?
Yes. This here is constant dimension. There's d square here. This is constant dimension.
You use what argument?
Well, let's see what I do. So I'm counting points in finite dimensional polytope. That's right. I can do that fast with Barinock. And okay. So, but next step is
Phi is the affiliate function.
yes. Well, it's just that projection here, really, from these things to these, and then you have to, have to put these ordering constraints in. But we don't do that now. Okay. The next step is that we got to understand. We have to understand this decomposition now, right? We want to now what we really want to count is the number of we really want to count this multiplicity function. So what we really want to understand is Vg lambda going to th now. But that I do in two steps. I first do Vg lambda, and I'm going to go to Tg, and then I'm going to go to Th, right? And I'm going to see, well, the first thing I already did before. So this gives me the Koska number I know from before, and it gives me this this Tg one-dimensional module, and now I have to reduce this here to Th, right? And I have to understand to which these betas here reduce, right? Which one this is. This is one-dimensional. If I reduce the action, it will stay one-dimensional, but I'll get a different one. Okay, and one can compute that. And what you find is that, what you find is, we're gonna abbreviate here a little bit. What you're finding is that actually you can write it again as like the gamma that you'll obtain here. So this here will be isomorphic to some VTH gamma, and the gamma fulfills again a linear relation with some fixed A that you have to apply to beta. Okay.
You do the sum over gamma.
Yeah, A is a matrix.
Right. A is a matrix.
TH.
A is a matrix I apply to beta, I get gamma. Okay, and now if I sort of if I continue that argument, then what I have a sum over gamma, right? With VTH gamma, and then here I have a sum over all the betas such that A beta is equal to gamma, and then I have the Koska coefficient. Okay. Note that this is not yet a partition function, because there are exponentially many betas here I sum over. Right, but I can write it as one partition function, because I can just write this as the number of points. One can easily show that you can write this as a number of points y and beta, such that phi of y is lambda and beta, and this A of beta is equal to gamma. It's basically you take your partition function from before, right? You put the beta in as a variable, and you put that restriction on. That restriction that A times beta gives you back gamma. Okay? And then you got again like a fixed partition function, one single partition function. And that thing you can evaluate fast. Very nice. And then we got the third step. Third step is of course the question, and that's how do I recover from the multiplicity function? How do I recover the multiplicities? Right? You know how to go from here to here. That's Weil's character formula, to go from here to the functions. And basically the opposite is just an inversion of Weil's character formula. I like to call this the derivative principle, but the lemma is the following. So if I'm given some representation V of, in our case now, H, then I can look at, it's not irreducible necessarily. I can look at the multiplicities. This here is the multiplicity function. This is the number of times an irrep mu occurs in V. This is the highest weight multiplicity. And I can relate it to the to what I call, so I call this now K lower bar mu. I would want it to denote that here by. But, so I have this weight, right? I managed to compute this weight multiplicity function with Barvinok. Now I want to get that thing back, and there is a really nice formula, namely, you can just take partial derivatives. Wait, finite differences, right? Because everything's finite. But so what is d alpha? So what is alpha? Alpha are in Lie language, these are the positive roots. In our kind of down-to-earth world, these are just vectors with a 1 at a position and then a minus 1 at a position later. Okay? And what is this d alpha doing? So d alpha applied onto my multiplicity function is just taking the derivative, right? So it's just doing k mu plus alpha minus k mu, right? That's a finite difference. I don't bother about dividing by anything. Right? That's a finite difference. So that's what this d alpha does. And of course, if you now apply this, the number of roots here, that is a constant. It's a constant because the dimensions, everything was fixed, the homomorphism was fixed. So there's only a finite number of such objects I need to do. And with a finite number of these differences, right, I can recover the multiplicity function from the weight multiplicity function. So I only need to evaluate Barvinok a finite number of times, and then I get my multiplicity. That's how it works. love to give you an idea of the proof of this, but I think I'm out of time. I think I'm out of time. So that's the idea. So there's these two small add-ons that I would have had. One is to tell you the proof of this, or at least an idea of the proof. You can ask me later in the break. And the second one is that actually this whole formula here is very much simpler even if you do the Kronecker. So it's even simpler if you do the Kronecker. So just a very simple kind of formula. So thank you for your attention.
Time for a few questions. So how does the formula look for the Kronekers?
Well, the partition function. So this basically for the Kroneckers, right? I start with a symmetric space, right? And in the symmetric space, the weights all come with like multiplicity 1. So I start with like this Koska function, which is just very super simple. It's just 1 or 0. So then I take the projection of that. So my k gamma A, gamma B, gamma C is actually just the number of points, and then I sum over these here are, this is sort of z to the d cubed, right? It's sort of like d cubed. I mean, it's like these are all here, and they're like d variables in each. And then you have the projections, and the projections suggest that you take two variables and you sum them together, and it gives you the if you sum the second two variables together, it gives you the projection. So you get gamma A, and then cyclic, right? If I take the first one and the last one, then I get gamma B. And if I take the first one and the second one and I sum over ijk, then I get gamma ck. And that is the partition function. And then the finite differences, these are just, right, the finite differences just correspond to adding a box and removing a box. So you just add a box and remove a box from these from this thing, right? And it's a in the two-row thing, you get 8 terms, right? You got to add a remove a box, add a remove box, add a remove box, all the 8 possibilities, or if you with like plus and minus signs. So this also immediately shows you that it's in gap P, because you can just collapse them, and then you have like these partition functions.
Yeah. So you said you include this for how many? What height it works?
Yeah, for 3.
Huh?
3 it works.
Oh, height of 3.
Yeah, height of 3. 4 doesn't work anymore. Well, maybe if one works hard, it can make it work.
Question maybe this software by Michael Walter. He uses Barbinock, he programs Barbinock, or he
uses the Barbinock library, I think.
There's some library that he uses.
Yeah, and you can also do the parametric version. I don't know how it works.
ISL library. ISL library.
ISL.
No, you really have to ask him. I'm not qualified.
Nicola.
There are algorithms for crystalline calculation.
Like?
Some software. And my question is simply, these classical algorithms is this algorithm better from a practical point of view, from a theoretical point of view?
Well, I mean, I don't know. I mean, you have to ask the practitioners, but I think in these libraries you can't do more than 100 boxes if you push it, no?
I mean, you cannot imagine how many boxes you actually.
You can do 700,000 boxes here if you like.
How many rows?
Of boxes.
You can do 10. You can do like 3 rows, right? You can do 3 rows, but you can easily do 10 to the 8 boxes. 10 to the 8 boxes. Like there's this example. I mean, if you go to Michael's homepage, he's got this example where he computes the number for, I think, 700,000, 400,000, and whatever, 100,000 maybe, I don't know. Don't ask me, something like that. That's a partition, right? First row length 700,000, second row length 400,000, third row length 400,000. And he gets the answer, yeah.
So it is from a practical point of view. So because
For fixed row length, right? For 3.
You can't do more than 3 rows, so.
Yeah, it can't go more than 3 rows, yes.
the class of the problem is
It's Sharpie complete. Like you have no hope, right? You have no hope of going for arbitrary row length. Of course, you may hope that instead of like 3 rows, you could do 4 rows or 5. But
was not before this one.
sorry.
The fact that the problem is Sharpie. I don't know the vocabulary, so I can't.
Yeah, it was known that it's Sharpie hard.
My general question is: could you compare this algorithm from a theoretical point of view with existing from the literature, the previous ones?
See, I don't know. In my opinion,
I think it was not clear that it becomes easy in quotes when you
In
fix
test or in every software from literary, there are algorithms computing.
yeah, I don't think any of them gives you more than 100 boxes. But I don't think any of them gives you more than 100 boxes, no?
Do more than 3 rows though, right?
They can do more than 3 rows, but I don't think they can do 100 boxes.
They can certainly not do more than 500.
Okay, they can't do more than 500 boxes. It was a qualified statement by the experts here. They can't do more than 500 boxes. I mean, I can only do 3 rows, but I can do 1 million boxes there.
Okay.
Yeah. Maybe it's known, but.
Come get me the